Morning, everyone. So over the last 2 days, we've been looking at two different ways of balancing redox reactions. We need to make sure we balance in terms of number of atoms, so mass has to be conserved. And we also, for our half equations, we can use electrons to balance off the charge. Note that in the full redox equation, electrons had to have canceled out using that lowest common multiple to make sure all the electrons that are oxidized, that have been lost, are actually picked up. Again, on a test, they just ask you to balance. You're more than welcome to do either half reaction method or oxidation number method. So I just want to give you a quick practice question, and then we'll move on in this chapter today. So the question would just say balance. I'll give you an equation here. We're going to go AuCl4 minus. This becomes C2O4 minus 2, becoming AuCl minus and CO2. Again, if it doesn't specify, you just do acidic. That's totally fine. Because they're not forcing you to balance one way or the other, you can do either half reaction or oxidation number method. I'm going to try to do both of them with you here so that you can make a comparison and see which you like better. I'd encourage you to pause the video before I show my work here so that way you can get some practice. Okay. So first method, let's practice here is let's try doing a half reaction method. This one here is a little bit harder because usually I have two things becoming two things. It's really easy to break up the half equations. Now I have two things becoming three. It's a little bit more obvious for half reaction method. Well, I have a gold compound. It's going to probably become gold, but the gold compound has chlorine inside of it. Probably the Cl minus has to be part of the same expression. So I'm going to have one equation, the AuCl4 minus becomes Au and Cl minus. I'll keep that in the same half equation. For the other equation here, I have my C2O4 minus, and this one here is ending up going to become just the other compound having carbon in it, CO2. Okay. So for half reaction method, our step was let's break up the two parts and then let's balance it. Remember, in terms of our steps, we're going to balance it major atoms first, anything that's not O or H, then O, then H, then charge. So looking at this here, just by inspection, I have one gold. I have 4 chlorines already. I need a 4 there. 2 carbons, that's just the first step, balancing your major atoms. We balance oxygens by adding waters, so I have no O's. In this case here, I have 4 O's, O's are good. Next, we balance for H's, so we have no H's, good. No H's, good. So actually, this was really nice. And then let's balance in terms of charge, so match up the number of electrons. Well, on the left side, my total charge is a minus. On the right side, every chloride here is a minus, but there's 4 of them. That gives you a 4 minus. That means I actually need to have 3 electrons on the left side. At that point, if your electron on the left side, we now know this is referred to as a reduction reaction. I would have had to gain those electrons. The reactant that was involved has been reduced. So AuCl4 is actually reduced. I would expect the other one to have the electrons on the right-hand side. Let's check it here. We have C2O4, sorry, I meant to say C2O4 minus 2. See, it's important to copy down it exactly here. I have minus 2 overall. In this case here, I have a net of 0. I'm going to add 2 electrons. There we go. We've lost electrons. It's on the right-hand side. The chemical that was involved, it's probably just the carbon part that actually lost the electron, but you still quote the entire compound. So we've matched up our half equations here. Not too bad. Then we do lowest common multiple. What do 2 and 3 both go into? Let's take this first equation, do it twice for every time we do the second equation 3 times. That sets it up so that the electrons cancel. I'm not going to bother drawing those electrons. And then we're going to put everything on the left, everything on the right, on the product side. So let's just copy it down here. I have AuCl4 minus. This one here becomes, so reacts with C2O4 minus 2. This becomes 2 Au. And sorry, I forgot to scale in the 3. So 3 C2O4 and 3 times the 2 that was already present. So 6 CO2. Okay. At that point there, everything should be balanced. The half equations were good, and then we just put it back together. Let me just check for the overall charge here. We have, oh, something's missing. So let's see, 2. Oh, I'm missing a 2. Really bad at scaling here. 2. I'm also missing the chloride. So always good to check, right? 8 Cl minus. And at that point there, everything should be matched up. Again, if you're running out of time, you just check for the overall charge. So the overall charge on the left side, every compound here is negative. There's 2 times that, so minus 2. Plus the negative 6 here, that gives you negative 8. On the side here, negative 8. We're probably good at this point. Okay. So that was half reaction method. It's very, very systematic, but it takes a lot of work. Let's compare that using oxidation number method instead. Okay. For oxidation number method, we need to do one extra step, which was, let's find the oxidation numbers of absolutely everything. So I know chlorine is a halide, is usually -1. There's 4 of them, that gives you -4. That puts gold in a +3 state. Later on, gold is like in a 0 state. You notice that the gold goes from 3 to 0. That's a -3. That means this has been reduced. You see that that -3 actually has something to do with behind the scenes, that 3 electrons that we're going to end up gaining. How about the carbon here? We have the oxygen here as -2. There's 4 of them. That gives you -8. 2 carbons minus 8 gives you -2. So therefore, the 2 carbons has to give you a +6. And therefore, every carbon is +3. On the other side here with CO2, the oxygen here is going to be -2 times 2. So -4. The carbon here is actually a +4. So we would expect 1 to go up, 1 to go down. That's what we get. The carbon actually goes up by 1. But remember, oxidation state is per atom. I actually have 2 carbons actually undergoing this change. This one here is already a +2. And you're already starting to see the 2 and the 3 sort of come into play. That's what tracking these changes in oxidation numbers are going to do. Before you do anything else, make sure your major atoms are balanced. So we have 1 gold, 1 gold. I had 4 chlorines. The chloride actually didn't change. I was in a -1 state. This is still in a -1 state. But I still need to have those 4 chlorines to make sure all the chlorines are accounted for. So let's put that as a 4. And then the carbons, I have 2 C's. I have only 1 C here. That's what made sure that I actually had double already. Okay, so major atoms first. Then you do lowest common multiple between the 3 and the 2. So very similar to here. Take everything involved in the -3. Let's times it by 2. Everything involved in the +2. Let's times it by 3. Okay. So with that in mind here, it's a little bit more tricky here because if I just take what's involved in the first half equation, the gold compound, if I scale it up by 2, that actually screws with the chloride as well. I'm going to pretend that the chloride is actually part of the gold equation. So even though gold is dropping by 3, just becoming gold solid, the chloride is also going to have to be scaled up by 2. So let's try it out there. Right, so we're going to scale it up by 2. I'm going to have 2 AuCl4 minus. For the other one here, it already was a +2. I need to scale it up by 3. So I'm going to have 3 C2O4 minus 2. This ends up giving you here 2 of the gold, 8 of the chloride, 2 times 4. And then I'm going to have 6, 3 times 2, CO2. And then at that point there, you just do a quick match. It's already balanced. Okay. Let's just check to make sure our oxygens are balanced. So we have 3 times 4, so 12 O's, 6 times 2, 12 O's. So I don't need to add any waters. I have no H's, so we're good. And there we go. We have a perfect match on both sides. Okay. So that just gives you a comparison. They're just going to say balance. Totally up to you which one you want to do. Okay. At this point here, I'm going to start introducing to you the redox table that we have in our data booklet. First thing to note is the font is really small. But just let me indicate this to you here. This table here is actually organized very similar to our acid-base table. We're going to have everything written as a reduction. So as I read from left to right, all of these chemicals are going to get reduced as I go left to right. While reduction, the gain of electrons, is sort of the reverse reaction as oxidation. If I refer to the other partner can actually come back at me, and that's actually called oxidation. So they're all written as reductions. That's why all of the electrons are on the left-hand side. If you ever want to read an oxidation, you take the partner and go backwards. Very similar to the acid was on the left. Acid equation donates a proton, versus if this is the conjugate base, it can then accept that proton again and go back the other way. So that's similar. We're going to talk about the standard potential part in a later lesson. But pretty much here, because every chemical has its own ability to reduce, some chemicals are going to actually reduce better than others. So just like we had acids having different strengths, we actually have the increasing strength of an oxidizing agent. Let's define that for ourselves. What do we know about an oxidizing agent by definition? It's a species helping another get oxidized. That's the definition. And usually we just note, but in doing so, by itself gets reduced. So that's perfect, right? We have reductions written left to right here. All of these guys here are trying to reduce and going forwards. And we actually have an increasing strength as I go up this way. So these ones here are actually the best at reducing, the best at gaining electrons, the best at going forwards. what does that mean about me going in reverse? If I'm really good at going forwards, my partner has a really hard time coming backwards, so these are going to be really bad. As my reducing strength here gets lower and lower, so as I get, it's getting harder and harder to actually go forwards, what's happening is my oxidizing strength is actually starting to get bigger and bigger and bigger, which is why we have the strongest. These ones here are going to be the best at oxidizing, right? Oxidation is going to be red right to left, and these ones here are the best. So lithium, calcium, a lot of metals are actually really, really good at oxidizing. So the strength, just like we had increasing strength of base, they're just going to quote it here. We actually have it as increasing strength as a reducing agent. As a reducing agent, I help something else get reduced. In the process, I typically get oxidized. Because of this sort of nature, what we're going to do throughout this chapter here, we're going to always start off from the really top left, the best guys that reduce. You're going to go down and you're going to end up finding your first match. Okay. So in this question here, I happen to have gold chloride. I find my match. I don't care if I have other things. I might have H+, I might have water, I might have aluminum, just totally making this up. If I already found who's best at reducing, this guy gets to do the reducing. The other guys are going to be spectators. The other guys just sit around. They're still in solution, but they don't get a chance to actually reduce. So that's starting off from the top left going downwards. Then that's only half of it. These guys gain the electrons. Who's willing to actually lose the electrons? I'm going to start from the bottom right. Those are the best at oxidation. Go up here. Again, depending on your problem here. Maybe I have manganese. Maybe I have lead. I have silver, right? By the time you find your first match, this is the guy that gets to do the oxidation. I don't care how many other guys you have in solution. Those guys are going to be spectators. And it's like that. We can actually find who's the best guy reducing, who's the best guy oxidizing, and that's going to be your overall spontaneous reaction. For the spontaneous reaction that we're going to look at over the next 2 days or so, we're going to find the reduction reaction occurs higher than the oxidation reaction, and we're going to find that when that happens, we have a spontaneous reaction. Towards the end of this chapter, we're going to do the same thing. We're going to start from the top left, the best guys at reducing. There's no such thing as a reducer, okay? So you still have to call it an oxidizing agent. But towards the end, we're not really going to have any of these really good guys at reducing. We're going to have the reduction occur maybe somewhere really low here. By the time we find oxidation, they would have crossed paths. And if they end up crossing paths, that actually is non-spontaneous. More on that later. So at least I wanted to introduce you to this table here, get used to sort of looking at this table. I know the font is a little bit tiny, so hopefully you can still see it there. These ones here are all written as half equations. Again, I told you they're written as reduction cells. You'll notice that they've already added the hydrogens, added the waters, added the free electrons. They essentially have given you, here's a half equation, here's a half equation, and all they're asking you to do then is maybe you might need to do a Lowes common multiple, maybe you need to put it back together, and then you can find the spontaneous reaction overall. Each of these equations here do generate some voltage. We're going to talk about potential here as relative to 0 volts for the hydrogen cell later on. But if this half cell has a voltage, the other half cell has a voltage, the comparison between these two half cells will end up giving you an effective battery that actually has some useful voltage to utilize. Okay? So let's just start looking into this table in a little more detail here. This section here is typically referred to as spontaneity. I want to know which reactions occur based on this table. And what we're going to actually do, we're going to actually look at in the past, they used to just call it an electrochemical cell. Nowadays, the electrochemical cell is an umbrella term. Electrochemical cell actually refers to, we're going to actually switch the language here. We're going to only look at a voltaic cell. A voltaic cell, how it's going to run, we're going to walk our way through it. Basically, we're going to run a chemical reaction. We're going to let something oxidize, something reduce, and as that chemical reaction occurs, this is going to actually allow for a flow of electrons, and this one here actually generates some positive voltage. So run a chemical reaction to produce voltage, and we're just going to call that voltage potential later on. This is a fancy name for a battery. This is how all batteries work out. Okay. So let's just try, for example, how do we tell that this is going to be a battery? Let's start off with a really simple cell here. So I have one single beaker, right? We're in water, we're in aqueous, that's why I was okay adding water. What I'm going to have is I'm going to have a copper plate, okay? So copper solid, and we're going to have an aluminum solid, aluminum plate here. Usually, throughout this chapter here, if you have a plate made out of copper, we'll probably also mix in copper ions. I have an aluminum plate here. I probably have some aluminum ions as well. We always want to put copper in a copper solution, aluminum in an aluminum solution, and we'll see why in a second. Okay. So I have those two plates here. Just some terminology for us. These two are going to be metals. These metal conducting plates are in general referred to as electrodes. Electrodes are metal conducting plates. So metals that can temporarily hang on to your electrons. Whoever wants to lose electrons, whoever wants to gain electrons here, the electrons are going to be deposited on these electrodes. Okay. So this is what I have so far. The question is, I want you to state the spontaneous reaction. What actually happens when you do this? Because we have all four of these chemicals, it's a good idea to make sure you know exactly what you have. So I have copper solid, copper plus 2 ions. I don't have copper plus 1. I have aluminum solid, I have aluminum plus 3. Because these ones here, one is elemental, one is charged, probably they undergo oxidation reduction. So what I want to do here is I want to look back at their electrochem table here. I want to see where these copper reactions show up and where the aluminum reaction shows up. Okay. So what we're going to do, I'm going to start off from the top left because these ones here are always the best at reducing. You're going to go down until you find your first match, right? By the time you end up running to copper, I see a copper plus, but like I said, I don't have copper plus. I need to skip it. I do see, however, we have a copper 2 plus, okay? So let me just write out that reaction for you here. Our equation says copper plus 2 gains 2 electrons. Although on the table it is written as an equilibrium arrow, if I find, nope, this is actually on the left side, I actually want this to go forwards, we're just going to do a forward reaction with copper. That occurs at a standard voltage. We'll just use this as a placeholder here, 0.34 volts. Okay. So I start from the top left. I found my first match. I don't actually run into aluminum until fairly far down the table. This one here is actually aluminum. So aluminum is quite a bit lower than it. Aluminum plus 3 could also gain 3 electrons, could also come forward and become aluminum, but you notice its voltage here is actually way less. We'll come back and we'll talk about why it's negative later on. But what we're saying here is, in the mixture, when we have both copper ions and aluminum ions, who's better at reducing? The copper plus 2, because it's higher on the left, this one here is actually better at reducing. This guy gets to do the reducing. Aluminum is out of luck, can't do anything. Okay. How about for the oxidation? Now, the oxidation, the strongest guys were at the lowest right corner. So we're going to start from the lower right. As I go upwards, this time I'm definitely going to run into aluminum solid way before I run into copper solid. So between these two, both of them potentially could have oxidized. Who's better at oxidizing? It's actually the aluminum. So where aluminum ions weren't good at reducing, aluminum is actually better at oxidizing. It's a stronger reducing agent. So this reaction actually goes in reverse. Okay. So those are my expressions here. I'm just going to copy those two equations at the bottom here. That way we can look at our cell in a little more detail. I found, looking at my chart, again, this is a general procedure. Start from the top left and go down, right? Because the top left are the strongest guys at reducing. I start going down this way here. I run into the copper equation. I just wrote this down for you earlier. One-way arrow once you find out what your match is. So it's actually the copper that's actually going to react. Then what you're going to do is going to start from bottom right. Start from these guys here that like oxidizing and go up. Find your first match. This is a general procedure. You start going upwards. We end up finding aluminum. This guy here is actually going to be better at oxidizing. Aluminum becomes Al plus 3 and 3 electrons. We just have to read right to left because that's actually the oxidation process. Okay. Well, notice again, the reduction reaction on the table occurs below the oxidation reaction. That's going to mean spontaneous. That's going to mean it actually happens. Okay. So let's just note down what happens in solution then. Between copper plus 2 and aluminum plus 3, copper plus 2 gets to gain electrons. Copper plus 2 gets to grab electrons. Aluminum plus 3 is a spectator. Meaning, aluminum plus 3 is just going to swim around solution. They're not going to actually do anything. It's actually copper plus 2 that actually grabs the electron, but that's only half. Who's actually willing to give the electrons? Between aluminum and copper solid, between these plates here, aluminum is better at ditching its electrons than copper. So copper is actually a spectator here. It actually doesn't do anything. So the real reaction that's happening here, you don't need to memorize this. You just want to look at the expression. We're actually taking aluminum solid. As aluminum solid jumps into solution, it's going to end up creating more Al plus 3s. That Al plus 3 has nothing to do with the Al that was already there. But as it produces Al plus 3, it's going to drop off 3 electrons on its plate. The copper plus 2, which is already in solution, happens to swim close to that metal plate. It's going to pick up those 2 electrons, and they're going to solidify out to become copper solid. Okay? So that actually is the redox reaction. That's the spontaneous equation. The electrons have been transferred. I can actually write out that equation for you here. If this was sort of half reaction method here, we have one that's a 2 electrons, the other that's a 3. Let me just show you one extra step here. So copper plus 2, 2 electrons. On the table, again, it was equilibrium, but once we've decided which way it goes, one-way arrow, I'm going to write the aluminum equation backwards. So aluminum actually ditches its electrons, becoming aluminum plus 3 and 3 electrons. Then what we can do is we can do lowest common multiple. What do 2 and 3 both go into? Well, I need to scale this first equation by 3, second equation by 2 here, and therefore we end up with 3 copper, 2 aluminum, ends up giving you 3 copper and 2 Al plus 3. While I have it on here, there were these voltages we'll talk more about in a later lesson, but the voltages here for the copper equation, it was positive 0.34. Every time copper plus 2 goes forward, positive 0.34. This one here, like Ka was talking about an acid strength on the acid base table, this negative 1.66 actually refers to how good aluminum is actually coming forwards. If I lose 1.66 going this way, what do you think is going to happen if I do the opposite? Instead of minus 1.66, when I reverse it, we're going to just flip the sign. So on the table, it was written as negative 1.66. This one earlier was 0.34. Instead of a negative 1.66, I'm actually going to have positive 1.66. So we end up flip the sign when the reaction is reversed. All the values on the table were written for reduction, going left to right. Now for aluminum, I'm rewriting it right to left. And instead of losing 1.66, I actually gain 1.66. Now this part here is a little bit strange here. Well, I'm actually scaling it up. I'm actually doing this equation 3 times, doing this equation twice. Long story short here, you do not scale up these voltages. And we'll end up with, this is a working battery. The working battery will have, first one gain 0.34, the other gain 1.66. And then you can just add up those 2 voltages. And total our battery when fresh, this one here gives me an exact 2 volts. Okay. The comment on how come I scaled up the equation, I definitely multiply by 3, I definitely multiply by 2. How come these ones here don't get scaled up? In fact, you're sort of right. Every time you run this statement, you're going to gain 0.34. So running this statement here 3 times actually gives you 3 times the amount of energy. Let me put some numbers to this. So if I ran that first reaction once, I get 0.34 for every 2 electrons. That's sort of run by in the equation. If I run this equation 3 times, you're right, I am going to get 3 times the voltage. 3 times 0.34, I'm going to get a total voltage of 1.02. But you'll notice when I ran that equation 3 times, I've also tripled the number of electron carriers. So if I take 1.02 divided by 6 electrons, we're going to find out by ratio that it actually is unchanged. So we're going to talk about this much more in a later lesson, but voltages stay constant. The ratio is constant even when scaled. Even when the equation gets multiplied, oh, this multiplied by 2, multiplied by 3, this voltage here stays constant, and there we go, we get 2 volts. We've been able to make some observations. The aluminum ions that initially were there didn't actually do anything. The copper that's sitting there, it isn't going to do anything. Now let's do 2 what ifs, and then I'll show you what a voltaic cell looks like. What if we had set it up here. I didn't know what my reactions were going to be. What if we had just copper solid and just aluminum, right? So just in pure water, okay? Again, you can check your table. You want to start from the top left and go down. You run into copper ions, you run into aluminum ions, but this time I don't have those ions. This time, both copper and aluminum happen to be on the oxidation side. Both of them are willing to ditch electrons, but if I have nothing in solution that's willing to gain those electrons, there would actually be no reaction. They can't both ditch electrons and jump into solutions. I can't both have an oxidation. In a similar fashion, if I have a beaker, what if I just had copper ions and just had aluminum ions? Now we had found these ones here on the left-hand side. Well, copper can reduce. It's better at reducing than aluminum. Copper is sitting around waiting for an electron. Aluminum plus 3 is sitting around waiting for an electron. If nobody's willing to give it an electron, we always have no reaction. So just an implication for you here. The reason why if we have a metal plate, we dunk it into a solution that has that ion, aluminum with aluminum ions here, is just to make sure there's one guy that's willing to gain electrons, one guy that's willing to lose electrons. Here's one problem as you set up this battery. We've been able to do the redox reaction. We've even been able to calculate, here's the voltage that the battery should be able to supply, but we have no way of actually tapering that electrical energy. The electrons too quickly get dropped off from the aluminum, the copper has already picked it up and it's already solidifying on the surface. I would have no electron flow, I have no current, I would have no way to actually generate useful voltage. What we're going to do is a little bit clever, and we'll end off with this. We're going to take this one beaker, and we're going to set up exactly the same equation. I do want to harness this 2 volts, but I want to force the electrons to go through a wire. As the electrons go through a wire, I can actually taper off that voltage. So what I'm going to do, I'm going to have 2 beakers instead of 1. We'll see why in a second here. I'm going to stick my copper plate again. Again, if I have a copper electrode, I'm going to put copper ions in solution. There probably will be some counterbalancing ions as well. Don't worry about them. I'm going to have an aluminum plate, aluminum solid. I have aluminum ions. So I have potentially one guy oxidizing, one guy reducing. We had already decided between the 2 guys that could reduce, copper plus 2 was better at reducing. Copper plus 2 is still going to be the reactive one. The aluminum actually just sits around doing nothing. How about for the oxidation? On the oxidation side, aluminum was lower on the right-hand side. Aluminum is better at oxidizing than copper. So between copper and aluminum, it's the aluminum that actually oxidizes. The copper doesn't oxidize. What I've done here is, because I know redox is actually sort of 2 half cells, I've actually allowed half the reaction to occur on one side. On the one side, aluminum jumps into solution and drops off its electrons. So aluminum, as a metal solid, it's going to jump into solution. It's going to end up creating more aluminum plus 3. That aluminum plus 3 has nothing to do with aluminum plus 3 that's already in solution. As it becomes a plus 3, it ditches its electrons on this metal plate here. Where do those electrons need to go to be picked up? Well, who wants to pick them up is actually copper ions. Uh-oh, the copper ions are actually in a totally different beaker. So what I'm going to do is I'm going to set up a wire. Right? This wire is going to let electrons flow. It's a conductor. It's going to let electrons flow from where they're being ditched with the aluminum, and they're actually traveling over to the copper side. The electrons finally arrive here, and then copper says, thank you. Copper plus 2 swims up close to the electron plate and then solidifies. The reason why we typically like making the plate also out of copper, I'm just solidifying copper ions on copper. And by doing this in 2 beakers, let me write this in words for you. By separating into the 2 half cells, by letting half of it occur in one, half of it occur in the other, electrons flow through. We typically call it an external wire. That's in red what I drew there. Through external wire in one direction, providing a direct current. All of electricity is electrons happen to be flowing. Direct current is flowing in one direction. That's what batteries do. AC current is charges that flow in 2 different directions. But because I'm actually forcing the electrons to actually travel, I can put whatever device I want to run, my voltmeter, my MP3 player, my buzzer, whatever you want, my light bulb. As the electrons travel from one side to the other, I'm actually able to taper off that electrical energy, where initially I actually had no way of doing it. It's the same reaction, but because I'm forcing the electrons to go through this wire, I can actually harness the electrical energy. That's where I put in my device. Now, a couple other side notes here. We had called these electroplates here, these metal plates here. They're temporary surfaces that hold electrons. The metal plate where oxidation occurs is referred to as the anode. It's actually where we get our language of anions from. Anode, by definition, is the site of oxidation. It's the whereabouts oxidation happens. The metal plate where the reduction occurs, the cathode, is actually the location, is the site of reduction. Again, another nice acronym for us here. We can say, oh, we had a friendly ox, and ox cared. Okay. Therefore, it tells us our anode is oxidation, our cathode is reduction. Okay. So now we've actually qualified a little bit. Electrodes in general are just temporary conducting plates here. They temporarily hold electrons, and now we have one that's the oxidation, one that's the reduction. One thing I want to be careful of in this definition, I'm just emphasizing this is the location of where the oxidation and reduction occurs. In this one here, sure, it was actually the metal plate that actually oxidized as well, but what about the cathode? Did the copper actually do anything? Well, no. Copper is just a temporary surface where the electrons arrive there. The reduction is actually because of copper ions. Copper ions end up reducing on its surface. Since this is still the location where the reduction occurs, the metal plate where this happens is still referred to as a cathode, even though the copper solid, so I can make a note here, copper solid doesn't do anything. It just temporarily provides a surface so that copper ions can actually reduce on its surface. Okay. So a couple other side notes here. We said electrons flow through the external wire. Because we now have the definition anode and cathode, electrons always flow. Electron flow from anode to cathode. They never jump into solution, but they're always in that direction. They're from where chemicals lose electrons, so loss of electrons, that's oxidation, to where they have to be picked up. So even as we do more complicated cells later on, electron flow will always be through this wire. Loss of electrons, gain of electrons. We can even make some observations for this at each side here. Well, remember the reaction involved aluminum jumps into solution, dropping off its electrons. So I'm taking solid material. As I jump into solution, I'm actually losing that solid. So therefore, we can actually conclude the mass, for this case, the mass of anode actually decreases. I actually lose aluminum because it's jumping off into solution. What about the mass of the cathode? Well, what's happening on its surface? On its surface, copper ions in solution are swimming up close to it, and they're solidifying on top of the metal plate, and therefore we can conclude the mass of the cathode actually increases. Again, you don't have to memorize that. You can just see that from the expression. Well, in the equation, copper ions solidify out as Cu, while on the other side, aluminum actually plates out. It actually becomes ions, so therefore I'm losing solid. Mass of solid actually increases. Sometimes mass is actually unchanged, so you have to test each particular cell. I need to make one last note here, and we'll leave it off there. One last note is if you did this, you put copper in a copper solution, aluminum in an aluminum solution. You set up the wire for the electrons to travel. This V here is actually where you actually taper off that voltage, actually use that voltage. Nothing's going to happen. The problem is, right now, we are proposing the one side is actually going to become more Al3 plus, more Al3 plus, more Al3 plus. This side is at risk of becoming overly positive. On the other side, I'm proposing copper ions. They pick up those electrons and they solidify. They grab on, they sort of solidify onto the metal plate because I'm losing positive charge at the moment. Let me write this down for you. So right now, as I propose it to you, right now, the copper half cell, so the half cell on the left, the copper half cell is in danger of becoming negative. Why negative? Is because it's losing copper plus 2. The copper is still around, it's just plated out as copper solid, it's neutral. And the other half cell, and the aluminum half cell, so the cell on the right, the aluminum half cell becoming overly positive. Why is it positive? Well, every time the reaction occurs, aluminum jumps into solution, becomes Al plus 3, more Al plus 3, more Al plus 3 here. This side here is going to get more and more aluminum. We're actually forming a lot of Al plus 3. Because I know charges in general are unstable, this reaction won't run spontaneously because it doesn't want one side getting positive, one side getting negative. So what our solution is, what's going to complete the circuit? What we need to do for a voltaic cell, for an electrochemical cell like this, we need to add one more piece of equipment. This piece of equipment here is going to be referred to as a salt bridge. And this salt bridge here, its job is just to minimize this. Okay, so here's our solution. We're going to add what's referred to as a salt bridge. Okay, it's a bridge containing a solution. Usually we say it's 1 molar KNO3. Even the K plus and NO3 minus might actually react, but we chose that chemical because it's so bad at oxidizing, so bad at reducing. You can check the table where they actually appear. Really low on the bottom left, really high on the top right side. Add a salt bridge to maintain, what's its job? To maintain electrical neutrality. Right? Because this salt bridge here actually has K as positive and NO3 as negative here, what we're going to have is the side here that was losing positive charge. What if I send more cations into that chamber there? Well, as I lose copper plus 2, I was at risk of losing positive. Whew, the K plus is going to make sure the positive is still there. What about this side here? Oh, it's becoming way positive. Let's send in my NO3 minus, it's a negative. As the NO3 minus swims into this solution here, it'll help to counterbalance the positive. That's actually able to maintain electron neutrality, and therefore we're going to have this conclusion here. Cations will flow to the cathode side, the K plus, ending up going to the cathode side, whereas anions will actually flow to the anode side. So I know we went through a lot of definitions here. Tomorrow I'm going to flesh out a few more of these voltaic cells. We will work a lot with this table in terms of spontaneous equations. Your job is to calculate, well, what's the voltage that we get, and we'll go from there. Right? If you have any problems, just let me know. Thanks, guys.